I'm Esteban Contero, and this is my conduction temperature profile project for heat and mass transfer. So here's the original scenario. We have a satellite in orbit. We're given a radius of 1.25 meters, thermal conductivity of 5. It's emitting radiation. Our emissivity is 0.75. It's also absorbing radiation, so its absorptivity is 0.10. And then our Q incident is 1,000, and then we're also given a midpoint temperature of just 0 degrees Celsius. And then we also have boundary conditions as well. So we have our symmetry because we have a spherical object, then our convection as well. So when we're solving this, we start off with the first law, and then we go to our heat conduction equation for our sphere right here. And then we want to get rid of this partial, so we take the antiderivative right here. So then we end up with this with C1, and then our R's also move up with values. And then we want to get rid of this dt to just t. So we take another integral, and we end up with this equation right over here. We apply our initial boundary conditions into our C1 and C2. So our C1, our C1 was equal to 0, and then our C2, the temperature goes to T naught right there. And we end up with that equation for our heat conduction. And then we jump to our radiation equation right here. So we have our Q total is the Q emitted minus the absorbed, right? So we break this down all the way down to where we solve for T. That's how we end up with that fourth root. And then once we have it solving for T, the surface temperature, we can plug in the equation we derived from earlier, right here, set them equal, and we can solve for our volumetric heat generation right here. After that, we plug our volumetric heat generation into this equation, and we're given everything else. We end up with that surface temperature. That's the also temperature distribution across the radius of the satellite. So we're gonna talk about parameter changes. So here's the first parameter change, increasing our thermal conductivity. So these are our temperature distributions across varying conductivities. So right here we have 5, 10, 15, 20, that's what we're changing. And what we can see is the best K value to get the best surface temperature for whatever radius that we want to design for our satellite right here. So you can see the higher K gives us a higher surface temperature at the outer radius than the lower K. Next, we have our volumetric heat generation change. So right here are our temperature distributions across varying heat generation. So we have 200, 300, 400, 500. What we can see right here is as our Q triple prime increases, we decrease that surface temperature at the outer tip or the outer radius. Parameter change 3. This is increasing that outer radius. So as you can see right here, I graphed the temperature and radius right here. As our radius increases, our surface temperature decreases. I have 1 meter, 2 meters, 3 meters, 4 meters. And as you can see, it follows the same temperature distribution. It follows this exact same profile as you just increase this. So we have our 1 meter. That's our trend line for 1 meter heading right there. For 2 meters, 3 meters, 4 meters. So what this tells us about our system and our ways we can change and design this for better utilization. So right now we have our first parameter change. So our surface temperature at the outer radius increases as the conductivity increases. So an application would be like using a material with a lower K if we want to lower that outside surface temperature, right? So for our second parameter change, the surface temperature decreases as heat generation increases. So we might want to increase the heat generation rate on the satellite if we want to decrease that surface temperature as well. Another thing, our last one that we played around with was increasing that radius. So if we want to like distribute more heat across the satellite to also decrease our surface temperature, we might want to increase that surface area. And that is it.